Okay. Any questions about the E1 mechanism that we talked about on Monday? Because we're going to continue on in Chapter 10 today, talking about E2. And then it seems as if the rest of Chapter 10 as well as Chapter 11 is kind of putting together SN1, SN2, E1, and E2. And I think we've done some of that, so it's probably a good part of that's review. But so we'll focus more on problems, and I do have, I think, I have a problem day at least, that may be Friday. We'll do some problems, or I'll write some other problems, and we'll go through that. So the chapter, what's next? Chapter 9. The Chapter 9 problems we'll make due next Monday. If you've already done them, then you got less to do. And then we'll figure Chapter 10 will be due maybe middle of next week or end of next week. So hopefully they don't all get stacked up at the end. But I'll put that on Canvas. I just updated last night, unfortunately, the Canvas. So it's at least the videos that are there. So I'm going to do what I do, a lot of what I'll do in the E2 video that I put in the textbook. But if you need to go back and look at it or look at the book, we'll do that. All right, so then I'm going to go back to E1 and compare E1 and E2 as well. So the second elimination mechanism is called E2. And so it's going to be bimolecular elimination, right? We had SN2, we had bimolecular substitution. We now have E2, which is bimolecular. And so one of these is obviously going to involve, I'll write the molecule that we worked with on Monday. We'll work with 2-chlorobutane. So when this was E1, the alkyl halide was the only molecule that was involved in the rate determining step. Because the rate determining step for E1 is still the formation of the carbocation. But now when we do E2, the question becomes, okay, it's bimolecular. What's the other molecule that's involved? And the other molecule is going to have to be a base. And it's going to have to be a strong base. And I'm going to start with using two examples of strong bases, sort of the extremes. So right now, let's just talk about it as base, B-. So B- comes in and it deprotonates a beta hydrogen. So that it comes in, grabs the beta hydrogen, the pair of electrons moves, and the chlorine leaves. So it's a one-step process again, just like SN2. And in this case, since B- could come in and grab either beta hydrogen A or beta hydrogen B, we're going to end up with two possible products. So let's write the transition state for HA being removed. So in the transition state, I'm going to have a bond between the base and the hydrogen, partial bond, because that's the bond that's forming. I'm going to have a partial bond between the carbon and beta hydrogen A, because that's the hydrogen, that's the bond that's breaking. The double bond is forming, so there's a partial bond there. And then there's a partial bond to the chlorine because it's leaving. So that corresponds to this red set of arrows, which would be HA. So that would be the transition state, minus the partial charges. So then, bless you, my question would be, where should the partial charges go? What partial charges and where should they go in this transition state? Ashton? Okay, the base gets a partial negative. And what else? Maybe, but if our final goal here, we should probably write the final product. Because the way we've been doing it is we've been averaging, right? So if that's our final products, it doesn't look like there's any need for partial positive charges and average between the reactants and the products. Although the reality is that hydrogen's leaving as being partially positive. It's being pulled off that way. But we don't necessarily need to put the delta plus there. But we do need one more partial charge. A chlorine with a partial negative. So we could say, yeah, the hydrogen could be delta positive. The carbons might have a little bit of positive charge, but not really in a formal sense. And if you want to put them there, that's fine. I'm not going to take points off for that. But really, the two essential ones are the base being slightly negative and the chlorine being slightly negative as leaving. So that would be the transition state for removing HA. The transition state for removing HB, in this case, would have a partial bond to the hydrogen, carbon-hydrogen, partial bond to the base, partial double bond forming, and then a partial bond to the chlorine leaving. So that's exactly the same, just exactly the same transition state, only to the other hydrogen, to beta hydrogen B. So then the partial charges would be in the same place. Delta minus on B, delta minus on chlorine. And then that final product would be so we get the same two products, potentially. We get the same two products that we got from doing SN1. So the whole idea of doing elimination is you got to find the alpha carbon, the beta carbons, and the beta hydrogens. And then you're going to form a double bond between the alpha and the beta carbons if there's a beta hydrogen that can be lost. Now that's going to get a little tricky here with E2. With E1, if you have a beta hydrogen, it can be lost. And I'll explain why and what the difference here is in E2 in a minute or 30. Okay. So if you're just writing the products, you identify the alpha, the beta, make sure the beta carbon has hydrogens, and you're going to form the alpha beta double bond. Right. So is everybody kind of with me here? So the difference between between E2 and E1 is now I have an active base coming in and ripping the hydrogen off and starting this whole process. Before, leaving group would leave, hydrogen would leave, end up probably attached to something else, but the something else didn't come in and violently rip the hydrogen away. The base is going to do that. The base initiates the process. So that's why it's got to be a strong base. Okay. Now, there is something about this mechanism, though, that is, the two mechanisms are different. And I'll show you the E2 mechanism first, and this is kind of laid out in the book as well. There is a geometry that has to be achieved for E2, and that is that the hydrogen that's being removed, the beta hydrogen and the leaving group, have to be anti-periplanar. And sometimes books use the term co-periplanar or periplanar. I always use anti-periplanar, and I don't even really need to do that because when we learned about Newman projections, anti meant that the hydrogen and the leaving group were in the same plane. So the beta hydrogen has to be anti the leaving group. And what that means is that if I'm over here looking down the carbon bond, that in my Newman projection, the leaving group is here and the hydrogen is there. So that really shows the anti of the anti-periplanar. So the hydrogen has to be opposite, has to be anti the leaving group. And the reason for that is to minimize the amount of orbital movement to form the final product. And what I mean by that is this, that if I have, and I'm just going to rewrite this structure, only that when the base comes in, grabs that anti-periplanar hydrogen, the pair of electrons moves here, and the leaving group goes there. That what I'm doing is I'm forming a double bond. Okay. And so I'm putting the bold and dashed wedges in, so it's like you're looking down, all four of those, or all six of those atoms are in the same plane. So you're looking at the double bond with the groups pointed towards you and away from you, and they're perpendicular to the screen. And we know that, we know that there's a double bond here. We know that what makes up that double bond, the orbital picture, looks like this. Those are sp2 hybridized carbons, and so that's our pi bond. That's the orbital picture of the final product. So the reason that we have to have the hydrogen anti-periplanar or anti, and not skewed or gauche, not periplanar on the same side, which would be eclipsing. The reason it has to be anti is because if you look at the orbital picture of this, your carbon's going to kind of look like that, and then over here the carbon that's attached to the leaving group is going to look like that. So if you think about how the orbitals are going to look, those are the two sp3 hybrid orbitals, including the little tiny orbitals that we only remembered about for SN2. So what has to happen with this molecule is, as the hydrogen is being pulled off and as the leaving group leaves, those orbitals have to go, let's see, like this. The orbitals are like this. What's going to happen is they're going to swing up and become parallel and then form the pi bond. If you can kind of see that happening in this picture. As the hydrogen is removed and the leaving group leaves, those two sp3 orbitals, they swing up, become parallel to form the two p orbitals that overlap to form the pi bond. And what happens, which I don't have enough stuff to do this with, is that my big lobe of my sp3, all of a sudden that electron density begins to shift down into the lower lobe. So as it moves, the top lobe is getting smaller, the smaller lobe at the bottom is getting bigger until when they're perfectly parallel to each other, you've got a p orbital with 50-50 electron density. So in order for a smooth movement to the transition state, you have to have those two orbitals aligned so that they can make that smooth transition. Because the more movement that I have to do of the atoms, the more energy it costs and the higher the transition state energy. So to get the lowest transition state energy, they have to be starting out parallel, or they have to start parallel to each other. And then that movement occurs. Can everybody kind of see that in their head? I think I have an animation program on my iPad. Probably take me 2 hours to draw something like that, but it's just, that's why it has to be anti-periplanar. So that's the orbital reasoning behind that. Maybe one of the videos in the book, they actually have done that. They have more time and money than I do. But that's why it has to be anti. Okay. Does that kind of make sense to everybody? So that's our restriction. When I said before, yeah, you're looking for a beta hydrogen, but it has to be a beta hydrogen that is anti to the leaving group. Okay. If there's no beta hydrogen that can be anti to the leaving group, it's not being removed. And they started with the most difficult situations, which are the acyclics in the book. So we'll do examples of that in a few minutes, and then into Friday and probably into Monday. We also have to deal with rings, but rings are easy. They should have started with rings, but instead they started with the acyclic molecules. Right. So that's the key restriction. The hydrogen has to be anti-periplanar. Now I want to contrast that with E1. Because in an E1 reaction, do I have that restriction? And hopefully the answer is no, because if I would have had that restriction, it probably would have been something that we needed to talk about on Monday. And since we didn't, it probably doesn't exist. And so here's why it doesn't exist. In E2, the second geometry will not react. Because the hydrogen, while being periplanar, is not anti-periplanar. But both of these will react easily in E1. Why? Because the first step in the mechanism is to break the carbon leaving group bond so that I end up with my carbocation. Now remember, a carbocation is sp2 hybridized with its empty p orbital. So once I lose the leaving group, I'm going to form the carbocation at that carbon. And the p orbital now is empty, but it's now parallel to both of those hydrogens. So all the hydrogen has to do, and you can kind of imagine the same thing, like here's my sp3 hybrid orbital here, and here's my sp3 hybrid orbital there. All that orbital has to do is be parallel to the empty one. And then it's going to swing up and donate both the electrons when the hydrogen is lost to form the double bond. But in this case, it doesn't matter whether the hydrogen started out anti-periplanar or periplanar. to the leaving group, because once the leaving group leaves, all the hydrogen has to do is be parallel to that empty p orbital. So both of these hydrogens can be lost. Where did that come from? So there is no restriction in an E1 mechanism. Because once you form the carbocation, all the hydrogen has to do is just become parallel to the empty p orbital, and you get it's lost as an H+. So the anti-periplanar geometry is only a restriction on E2, not on E1. Everybody okay with that? So that's the geometric requirement of E2 that's not there in E1. So as long as you have a beta hydrogen in an E1 mechanism, you're going to lose it. If you're doing E2 with the base, then that hydrogen has to be anti-periplanar. So is it possible that you may have a beta hydrogen that's not anti-periplanar? Yes. And you won't lose that hydrogen because you can't form that transition state. Right. With me? So let me go back here. Let me go back to product A and B. So what did we do on Monday? When we did this reaction by E1, our next thing was, okay, what's the major product of this reaction? And if this was an E1 mechanism, what would be the major product? And let's put that up on the let me go ahead and just let you answer that so that gets everybody awake, although it's getting tougher and tougher every day. I just need a day off. So on Monday, if this was E1, which one would be the major product, A or B? And I'm looking for 100% correct. Okay, I counted 28 people here, so is there anybody who didn't get a chance to answer? (26 A's). So when we do E1, the major product is the product that is most substituted. And that product is A. Now, I think I have a reason why people may have chosen B, but we'll get into that. How about E2? Well, I'll make that a rhetorical question, which means I will answer it. Unless you want to jump in and answer it, which I will certainly let you do. But what about E2? Is it going to be A or B? And the answer is It depends. And your question should be, on what? What's it depend on? Well, it's going to depend on the base. So now let's talk about bases. Because so far I just said, oh, B minus. But we have some choices of B minus. Our real restriction here is that we need to use a strong base. Now, my choices of strong bases are going to be alkoxides or, so this is an alkoxide, it's called the protonated alcohol, and this is called an amide, not to be confused with the amide or amide of carbonyl chemistry that you use to make proteins out of, and amino acids that come together to make amides. This is a different kind of amide. And so these are really my two choices. Hydroxide, not so much. Because here's the problem with bases. Strong bases are also strong when there's long periods of silence after my question. That's not rhetorical. You can jump right in. Strong bases are also strong nucleophiles. So if I want a base that deprotonates. I don't want it to be a nucleophile. Because now I'm going to be in competition, right? If I want to do E2, I don't want to do SN2. So I want my base to be a base and not a nucleophile. Because the tendency of these molecules is they attack first. They try and do substitution first, and then when they can't do substitution, they turn around, they get angry, and they rip off a hydrogen from the molecule and do E2. If we give them personalized characteristics, which they don't have. Okay, they're always trying to do SN2 first. And then when they're not, they just rip a hydrogen off and we do E2. Okay. Not exactly true, but hopefully it gets the point across that you remember that. So the problem with alkoxides is that alkoxides love to react as nucleophiles. So I have to stop it from acting as a nucleophile. And the way to do that is to take advantage of the same principles that we used in SN2 to determine reactivity. If I use a small, like CH3O-, which would be called methoxide, that's going to be a strong nucleophile. If, on the other hand, I attach a tertiary-butyl group to it, this is called Tert-Butoxide. It's a base. So what I do is remember that tertiary alkyl halides cannot undergo SN2 because they're too sterically hindered. What I do is I take that principle and I say, if I make the base sterically hindered, it can't act as a nucleophile anymore. And so then it must act as a base. And so this takes the gray area out. Tert-Butoxide, always a base, always going to do E2. And there are some other sterically hindered amide bases that you can use. I don't know if they show them in the book. The state-of-the-art ones are things like this. This is called diisopropyl amide. And the counterions are not important. Well, they are important, but not in this class. I can't just go down to the stockroom and say, hey, give me a bottle of Tert-Butoxide, because they'll say, well, what kind do you want? Do you want sodium? Do you want lithium? Do you want potassium? they always have to have an alkali metal. So typically we use potassium. So it's potassium Tert-Butoxide. With the diisopropylamide, it's normally a lithium. So this is sometimes abbreviated LDA for lithium diisopropylamide. My favorite, which I've done a lot of research on and published a few papers here and there on, is this one, which is called LIHMDS for lithium hexamethyl disilazane. And it's really sterically hindered. I like that one because you can make it in the sodium, in lithium, sodium, potassium, and even cesium flavors. And you can also do NMR, which we'll learn about next semester, on them. And all of those are very nice because I can crystallize them and I can make them super pure and do things with. But they all have a characteristic of strong base, but they all have to be sterically hindered. So these are all going to be examples, and we're just going to use potassium Tert-Butoxide, but these are all sterically hindered strong bases. So again, I'm using fundamental principles here. I don't want it to act as a nucleophile. I want it to act as a base. The way to make it act as a base is to make it sterically hindered. Now, there are going to be consequences for that, but they will act as bases. Okay? So we're going to focus on potassium Tert-Butoxide. And 9 times out of 10, I probably won't even put the potassium in there, because when I put the potassium in there, it's nothing more than a counterion, but people don't recognize that, so it ends up everywhere. Like, it'll end up in the middle of a cyclohexane ring. I don't know what it's doing there. But counterions, you have to realize counterions are just counterions. They go wherever the negative charge is. But, so in order to avoid point loss, I usually don't involve the K. So we just use potassium, we'll just use Tert-Butoxide. So that's one way to have a strong amide. There's another one that I use in problems, and that is NH2 minus, which is simply amide. Now, it's small, but for reasons that I'm not going to get into, and don't ask me because I'm going to have to make something up. And it may sound good, it may not sound good, because I'm not quite sure I fully understand why it won't do this. But amide itself is, it is not nucleophilic. And it might just be because of its solubility, because only enough of it dissolves to actually do something productive. But it is small, but it's not nucleophilic. It acts totally as a base. So these are my two extremes. I have a small, strong base, and I have a sterically hindered strong base. And that's all I need. I need those two extremes. Okay. So these are the bases that we're going to use with E2. How do you know if a reaction's E2? It's got one of those two bases in the reaction. If those two reagents aren't there, it's not E2. It's as simple as that. So, is everybody kind of okay with that? So you just have to kind of accept that amide will be protonate and has no real intention of doing substitution. So now let's go back to my original problem. My original problem was that I was taking 2-chlorobutane, doing an E2 on it to form these two products. products A and B. And I'll come over here because I can erase easily. I'll put in my HA and HB. And I forget which one of these two products is more stable. I really don't forget, but which one of these two is more stable? A. So A is the more stable product. We have to keep that in mind. And I said that if you're going to do E2, that the major product of the reaction is going to depend on the base. So here's how that works. And I don't know, I'll start with Tert-Butoxide. So if you're going to do this reaction with Tert-Butoxide, the Tert-Butoxide has to come in, grab the hydrogen that's antiperiplanar, go through the transition state, kick off the chlorine, and form the double bond. If I asked you and said, now, this big sterically hindered Tert-Butoxide, which hydrogen do you think it's going to be easier for it to deprotonate? HA or HB? Why B? You mouthed it. Okay, it's on the end of the molecule. Let's be a little more precise. What kind of hydrogen is that? Primary, secondary, or tertiary? Primary. So HB is a primary hydrogen. What kind is HA? Primary, secondary, tertiary. And hydrogens are the same degree as the carbon they're attached to. So HA is what kind of hydrogen? Secondary. So it's a secondary. Primary, secondary, and tertiary is one of those key concepts that we keep using over and over again. So which hydrogen is the Tert-Butoxide going to be able to get to easier? The primary one. I could restate that and say the Tert-Butoxide is going to be able to get to the primary hydrogen faster. And so here's something funny. The Tert-Butoxide is going to make product B. But product B isn't the most stable product. Oh no, this is not a Hammond's postulate thing. Right? We can't use Hammond's postulate to predict that reaction. But we can make sense of it in terms of the reaction coordinate diagram, if we'd like to, and we like to. So if I'm looking at this, here's what happens. I've got two possible transition states that the reaction could go through. Which transition state's going to have the lower energy? The Tert-Butoxide removing the primary hydrogen or the Tert-Butoxide removing the secondary hydrogen? Which one's going to require less energy? Maybe we should throw that out as a question. Let's throw that out as a question. Which means, unfortunately, I have to remember what I just asked. So we're going to use HA and HB here. So HA is secondary, HB is primary. So here's the question. The question is, I'm drawing the transition state energies for those two reactions. The Tert-Butoxide coming in and grabbing HA and grabbing HB. Which one has the lowest overall energy? The transition state for grabbing HA or the transition state for having HB? HA being secondary and HB being primary. Which one is going to have the lowest transition state energy? And then we'll label these two transition states. Going once, going twice, almost going 3 times. Okay. All right, 26 people say B. So because of the steric hindrance, it's going to be easier to get to HB. What does easier mean? It means having a lower energy. So this would be removing HB. That transition state would be removing HA. Because for the Tert-Butoxide to go into the middle of the molecule and remove the hydrogen, there's going to be more steric hindrance. Okay. Now, normally when we're doing Hammond's postulate stuff, the lower transition state goes to the more stable product, right? But in this case, it's exactly the opposite. It would look something like that. Because B has a higher energy than A. And the important part here is, if you want to go down the rabbit hole of talking about energies, which, you have to do because that's what drives chemistry is energy. Money drives everything else, but chemistry is just driven purely by energy. The transition state energy is what drives this reaction. Now, in the book, they're going to call this a kinetic product. And I think we talked a little bit about that in the past, but what I've learned is what we talked about in the past, we need to talk about again and again and again. So kinetic means the product that's first formed. And how does the product that's first formed, how do you get that product? You get that by having the lowest transition state energy, because of the Arrhenius equation. No Hammond in this case, just Arrhenius. So this would be called the kinetic product. I wondered in the book why are they including kinetic versus thermodynamic? That's a second semester topic. And we talked about the second semester application of that before. But that's why they're talking about it here. Because when you use a sterically hindered base, the transition state energy of removing the least sterically hindered hydrogen is going to be lower, and that's what's going to happen. So that's the product that's going to be formed first. And if you do remember when we talked about this before, what we said was you always form the kinetic product first, but then there was a reversible reaction that got you back into the middle so that you could form the other product. There's no reversibility here. Once you're at the kinetic product, you're done. So sterically hindered bases form the double bond that is least substituted. And I don't even like that term, because what I like is the sterically hindered bases remove the least sterically hindered beta hydrogens to form that product first. So that's the major product of that reaction. From where?
About the sterically hindered.
Okay. So the sterically hindered bases remove the least sterically hindered beta hydrogen. That's the best way to think about it. So the sterically hindered bases remove the least sterically hindered beta hydrogen. Now, that least sterically that least sterically hindered beta hydrogen must be able to go anti-periplanar. It still has to be able to go anti-periplanar because if hydrogen can't go anti-periplanar, it ain't deprotonated in E2. So it still has to go anti-periplanar. But the reason that that one is removed ultimately energetically is because the diagram looks like that, and it's the transition state that's the most important. Now what about a non-sterically hindered base? Well, if we think about a little base, small base, is there that much difference between it deprotonating the secondary and the primary? A little base can go both places almost equally well. There may be a slight energetic difference, but for the most part, the transition state energies are going to be almost identical. So if we drew that diagram out, it would look something like this, where now you have B and A, but the two transition state energies are virtually identical. Small base can get to either hydrogen the same. So if it can get to either hydrogen the same, what's going to be the driving force of that reaction to form the most stable product? So this would be sort of the diagram of a small base, and this would be the diagram of a sterically hindered base. So what that means is that if you want to form B, use Tert-Butoxide. If you want to form A, use NH2 minus. For those reasons. And we're going to have to begin to think about not only writing products, but making the products we want. Most organic chemistry is broken up into two things. People that study mechanisms, which is sort of where I have been through the years, which is called physical organic chemistry, which takes the physical chemistry and merges it with organic chemistry. And there's a reason why people don't like physical chemistry or organic chemistry. Double that and you get physical organic chemistry. Or there's people who do synthetic chemistry who just make stuff and they don't care how the reaction occurred. Well, we always need a yin and a yang. We need a reagent that'll make this product, but then another reagent that'll make this product. It's exactly opposite. And so the Tert-Butoxide NH2 minus is that pair. You want the most substituted double bond? NH2 minus. You want the least substituted bond? 9 times out of 10. You want the least substituted? Go ahead and use the Tert-Butoxide. Now remember what I said earlier, and then I'll shut up and you can leave. It removes the least sterically hindered hydrogen. 9 times out of 10, that'll be the least substituted double bond. But not always. So that's why I said it that way as opposed to saying it's going to form the product. Okay. So on Friday we'll continue this. I'll bring some problems that we can do. We still have to talk about rings. Well, we still have to talk about open systems, which I know there's a lot of problems in Chapter 10 on. We'll do those on Friday as well as talk about rings. So I won't have any homework assignment. You can get caught up on all your problems from Chapters 9 and then what you can do in 10. And I'll update the website, I'll update Canvas today as well.